All right, let's try some examples involving centripetal acceleration and circular motion. One of the most important applications are vehicles making turns on either flat or banked roads. We'll discuss both right here. First, let's think about a car making a turn on a flat road. What force allows you to make that turn? Think about driving in the winter when there's ice and water on the road. You come to a turn in the road, you turn the wheel, but nothing happens, and you skid straight ahead and go off the road. Your car is obeying Newton's first law. The car is going straight and wants to continue going straight. There must be a force that allows the car to change its direction of motion. In other words, to follow the circular path of the turn. In this case, that centripetal force is friction. Friction is our friend here. Note, we didn't add another force in the problem. Rather, we used the forces that were in the problem, in this case friction, and that became the centripetal force. Anytime you have a force that's directed towards the center of a turn or of a circular motion, that's going to be the centripetal force. So here's a picture of a track. Here's a car. We're looking at this track from above. The car is going clockwise around the track. We're looking from above. This picture, unfortunately, makes it difficult to see everything that we're looking for. This black arrow represents the car's velocity, and then this red arrow is going to represent the car's acceleration. Note that that's directed towards the center of the turn. I'm going to redraw the picture so I can see the forces acting better. I'm going to rotate the picture 90 degrees so it appears that the car is going into the paper at that particular instant of time. So here's my car, here's my flat surface. I'm going to simplify things a little bit. You know that cars typically have 4 tires. That means there'd be 4 contact points on the ground. That means there would be 4 normal forces, but I'm going to group them together into one normal force. Same thing with the frictional force. There's actually 4 such forces, but I'm going to group them all together into one frictional force. First of all, here's gravity, and then here's the frictional force. I'm going to follow my 5-step process. I drew a picture. I ID'd all the forces. I'll define a coordinate system like I normally do, and then I'll write N2, Newton's second law, for both the x and y directions, and then I'll solve for things. The frictional force is directed towards the center of the turn, therefore it is the centripetal force in this problem. Here's my y equation. The normal force minus the gravitational force is equal to MAY, but that's 0 because my car is a car and not a bird. It's not flying. Here's my x equation. This is a little bit different. The frictional static force is equal to ma sub c, but we knew what a sub c was before, so that's mv squared over r. Since there is friction, I have to have another equation. That's the frictional constraint. In this case, the frictional static force is going to equal mu sub s times F sub n. Now, why am I using F sub or mu sub s? In other words, what kind of friction do we have here? You may think it's kinetic friction, but the car is moving, but the tires are rolling, not skidding. So while they're rolling, they are momentarily at rest with the road. The car is not moving in or away from the circle or towards the circle, so we can say that it's momentarily at rest. Therefore, we're going to use static friction. Now we can solve. Solving is the easy part. It makes sense to do these calculations in general so that we're solving the problem of a car of any mass, of any radius, at all velocities, and all coefficients of static friction. Here are my equations again. I can solve for f sub g, that's easy. F sub g is just equal to mg. Then using my f sub y equation, I find that the normal force is equal to the weight of the car, or mg. I can use my expression for the normal force to find the frictional static force. I find that the frictional static force is equal to mu sub s times mg. Finally, using our expression for the frictional force in the x equation, I get the following result. Mu sub s mg is equal to mv squared over r. Here's where a miracle occurs. Notice that the mass, m, appears on both sides of the equation. I can cancel them out, eliminate it from the equation. That should make sense. When you go around a turn, if you've ever seen speed limit signs for turns, it's not dependent upon mass. Mass must cancel out. It can't be an important part. So I get this final result that mu sub s gr is equal to v squared. This is our general equation. This equation is always true. I would much prefer that you're able to derive it by drawing a picture, identifying forces, defining coordinate systems, and so on, following our procedure, than to just memorize it. It does come from our 5-step procedure. This equation does relate the speed, v, the radius of the turn, r, and the coefficient of static friction, mu sub s. This is the equation that engineers use to design roads, particularly things like cloverleaf interchanges on expressways. You can use this equation given a particular velocity or a particular radius or particular coefficient of static friction and find for the unknown quantity. Here's a numerical example to show how this could work. Consider a cloverleaf exchange. You've probably driven on these on the freeway. Assume that the turning radius of the cloverleaf is about 75 meters and the coefficient of static friction between good tires and dry pavement is 0.7. What is the maximum speed one could go without slipping off the road? I'll use the equation that we had from before and I'll solve for v. Putting in the numbers, I find that 525 is equal to v squared. That means v is 22.9 meters per second. If I convert that, I get 51.3 miles per hour. You probably don't want to take a turn going quite that fast. This is about the right size for a cloverleaf, and these are under the best conditions. The posted speed that the engineers or the designers usually put on is about 60% of the maximum just for safety reasons. Also know that if the pavement is wet, like with rain or snow, mu sub s could be as low as 0.10, which means that you can easily slide off the edge of the road if you're not careful. Again, it's important to know that this equation involves 3 variables. So if the engineers can determine or pick 2 of the variables, they can easily calculate the third. Now, have you ever watched the Olympics and seen the bike races on the track? They ride in something called a velodrome, which is a steeply banked track. Similarly, NASCAR racetracks are also banked. If you've ever been to the Chicago Raceway, you may see that it can be a fairly steep bank. Drivers use this bank to provide a force which is directed towards the center of the circle and aids in making the turn. Let's do a banked road problem. We're going to simplify it though, because otherwise it gets really complicated. We'll assume that there's no friction. It's really not very realistic, but for first purposes, it makes sense. If we have both a bank and a friction in the problem becomes very hard. Friction can act up the incline if the car is going too slow and is sliding down the bank. Or it can act up the incline if the car is going fast enough. Or down the incline, sorry, if it's going fast enough. So it becomes a very complicated problem. So let's go right to the rotated picture. The roadway is going to be inclined at an angle theta. So here's my car on the inclined bank of theta degrees. I've got gravity acting down, the normal force acting up. No friction in this case. We're simplifying things to make it a little bit easier. Wow. Ooh. First of all, let me define my coordinate system, and then you'll see that I had to resolve the normal force into the x and y components. Why did I pick this one and not the slanty coordinate system? Well, it turns out that the component of the normal force, the Fn sine theta, directed in the x direction, is directed towards the center of the circle. We typically want to define our coordinate systems so that the acceleration is along either the x or y. In this case, our acceleration towards the center, causing the car to turn, will be directed along the x direction. I'll do the 5-step process. As I mentioned before, we changed our coordinate system. The centripetal acceleration is going to be along the x-axis. Our N2 equations then become the following. Fn cosine theta minus Fg is equal to ma sub y, which is 0 because it's a car and not a bird. And then my x equation, Fn sine theta, is equal to the mv squared over r. Note that the component of the normal force in the x direction, the Fn sine theta, is the normal force. Now we solve. Our x equation stays the same, and we know that f sub g is equal to mg. We can put that into our y equation, giving these two equations. Fn sine theta equals mv squared over r. Fn cosine theta minus mg equals 0. I'm going to solve for the normal force in the second equation. So I know that Fn is equal to mg divided by cosine theta. I'm going to put that expression for the normal force into the first equation. That gives mg sine theta over cosine theta is equal to mv squared over r. Notice that the masses again cancel on both sides, the miracle that we saw before, and that the sine of theta over the cosine of theta is tangent theta. Canceling the masses, replacing with tangent theta, I get g tangent theta equals mv squared over r, or if I simplify it a little bit, v squared is equal to the quantity gr times tangent theta. Like the unbanked turn equation, the banked turn equation relates the three variables together: velocity, or speed, the radius, and in this case now theta. Here's an example. Consider a racetrack with a turn of radius 125 meters. A race car takes a turn at 60 miles per hour. What angle should the track be banked at? Again, in this particular case, the only thing allowing my car to make the turn is going to be the incline of the track. If we added friction, we get a more realistic value, but that math is kind of hard. First, I convert the 60 miles per hour into 27 meters per second, put it into my equation, and I find that my angle is going to be about 30 degrees. That seems to be about right. Hopefully, you'll see that these two examples, either the banked turn or the unbanked turn with friction, are really good examples that make use of our centripetal motion.